In the fall of 1984, workers inside a General Motors engine plant watched another batch of V6 engines roll off the assembly line. There was nothing glamorous about them. No polished aluminum valve covers, no screaming red paint, no race-winning reputation, just cast iron, 6 cylinders, and a simple mission: keep working no matter what. Most people never gave this engine a second thought. But what almost nobody knows is that this ordinary-looking V6 would outlive nearly every famous American engine of its era. It would survive the fuel crises, emissions crackdowns, OBD2 regulations, drive-by-wire electronics, and even the rise of turbocharging. It would power millions of trucks, vans, SUVs, boats, and industrial machines. 40 years later, versions of it were still being built. So how does an engine designed during the Reagan administration outlive engines that were supposedly more advanced? You think you know this story? Not like this. To understand why the 4.3 Vortec became one of the longest-running engines in GM history, you have to go back to a time when America was obsessed with one thing: the small-block Chevrolet V8. By the late 1970s, Chevrolet's legendary 350 cubic inch V8 had become the backbone of the company. It powered pickups, muscle cars, family sedans, police cruisers, and countless boats. Mechanics loved it because every bolt seemed to make sense. Owners loved it because it refused to die. The small block V8 had earned a reputation that bordered on legendary. You could find it in Manhattan taxicabs, in Montana ranch trucks, in Florida bass boats, in California hot rods. Everywhere you looked, the small block was working, proving itself, day after day. But there was a problem. Fuel prices had climbed dramatically. Government emissions regulations were tightening, insurance companies were punishing thirsty engines. Customers still wanted truck durability, but they no longer wanted V8 fuel bills. The 1979 energy crisis had changed everything. Gas stations ran dry, prices doubled seemingly overnight, lines stretched for blocks. Americans suddenly cared deeply about fuel economy. Words like miles per gallon became dinner table conversations. GM needed something different. Not an entirely new engine, something cheaper, something familiar, something that could be built using existing manufacturing equipment. The automotive industry was facing tremendous pressure. Japanese trucks were gaining market share with smaller, more efficient engines. Ford was investing heavily in new designs. Chrysler was fighting for survival. GM's bean counters looked at the numbers. Developing an all-new engine family could cost over $1 billion. Retooling factories meant shutting down production lines. Training mechanics required massive investment. Building supplier networks took years. There had to be a smarter solution. Instead of starting from scratch, Chevrolet engineers made an unusually practical decision. They simply removed 2 cylinders from the famous small-block V8. The result appeared in 1985, the Chevrolet 4.3-liter V6. Officially displacing 262 cubic inches, the engine measured 4.00 inches of bore and 3.48 inches of stroke, the exact same dimensions as the 350 V8. The cylinder bank angle remained 90 degrees instead of the smoother 60-degree layout used by many V6 engines. Compression ratios initially hovered around 9.3:1 depending on application. At first glance, that sounded like a compromise, and in some ways it was. A 90-degree V6 naturally creates uneven firing intervals. Without engineering changes, vibration becomes a major issue. The math simply doesn't work perfectly. 6 cylinders in a 90-degree configuration creates inherent balance challenges. GM's solution was clever. They redesigned the crankshaft with offset crank pins, creating evenly spaced firing events that dramatically improved smoothness while allowing the engine to share many production tools and components with the V8. Those offset journals were precision balanced. Every crankshaft was individually checked. Balancing weights were carefully calculated. The result wasn't perfectly smooth like some luxury V6 engines, but it was smooth enough. And crucially, it worked. That decision saved millions in manufacturing costs, and it would shape the engine's future for decades. The part-sharing strategy went deeper than most people realize. Pistons could be manufactured using similar processes. Connecting rods shared design language. Cylinder heads used familiar valve geometry. Even the casting molds could be adapted rather than completely replaced. Assembly line workers already understood the architecture. Suppliers already produced compatible components. Dealership mechanics already knew the basic layout. This wasn't just engineering cleverness, it was business brilliance. But building a cheaper V6 wasn't enough. It had to prove itself where American buyers cared most: pickup trucks. The early versions produced around 155 horsepower and roughly 230 pound-feet of torque, depending on emissions calibration and fuel system. Those numbers weren't exciting. Compared to the V8s everyone loved, they seemed almost disappointing. Magazine reviewers complained about the lack of muscle. Enthusiasts dismissed it as a penalty box engine. The kind of motor you got when you couldn't afford what you really wanted. But torque arrived low in the RPM range, exactly where truck owners needed it. Whether hauling lumber, pulling a fishing boat, or climbing muddy trails, the 4.3 delivered dependable pulling power instead of flashy horsepower numbers. Peak torque arrived around 2,400 revolutions per minute, not at screaming redline, right where truck engines spent most of their working lives. Then reality arrived. Contractors overloaded them. Delivery drivers idled them for hours. Farmers abused them every day, and somehow they kept running. Mechanics began noticing something unusual. Engines with 200,000 miles still maintained respectable compression. Timing chains stretched slowly. Bottom ends rarely failed. The thick cast iron block barely seemed to notice abuse. One fleet mechanic in Ohio reportedly joked, "The truck falls apart long before the engine does." That wasn't entirely an exaggeration. Construction workers told stories of trucks with rusted-out beds and failing transmissions, but the engines still running strong. Landscaping companies reported similar experiences. Trucks that looked absolutely beaten cosmetically would fire up every single morning without complaint. The 4.3 wasn't winning beauty contests, it was winning something more valuable: trust. But GM wasn't finished. The real transformation came almost a decade later, and that's when the engine earned the name nearly everyone remembers: Vortec. In 1996, Chevrolet introduced the Vortec version of the 4.3. Most people assume Vortec simply meant bigger horsepower. The truth was much more interesting. The cylinder heads were completely redesigned with higher flow intake ports and a more efficient combustion chamber. Better airflow meant improved cylinder filling. Better combustion meant more power from essentially the same displacement. Engineers used computational fluid dynamics to optimize port shapes, something that was cutting-edge technology in the mid-1990s. Combustion chamber design incorporated modern understanding of flame propagation. Sequential central port fuel injection replaced earlier systems on many versions, dramatically improving fuel delivery precision. Instead of batch-firing injectors, each cylinder received fuel at precisely the right moment. Air-fuel ratios became more consistent. Throttle response improved noticeably. Emissions dropped significantly. Compression ratios climbed to around 9.2, while maintaining regular gasoline compatibility. Horsepower jumped to approximately 190. Torque increased to roughly 250 pound-feet. That may not sound extraordinary today, but in a mid-1990s compact pickup or full-size work van, it completely changed the driving experience. Acceleration improved. Fuel economy stayed competitive. Cold starts became easier. Emissions dropped significantly. The engine hadn't become revolutionary. It had simply become better at everything. Owners who upgraded from earlier versions immediately felt the difference. Merging onto highways became less stressful. Passing slower traffic required less planning. Towing moderate loads felt more confident. Most people don't realize just how much engineering went into making an old design survive a modern world. Every single component was re-evaluated. Valve springs were tested for millions of cycles. Piston ring tension was optimized for modern oils. Head gasket materials were upgraded, but there was another challenge: heat. Under heavy towing, localized hotspots developed around the combustion chambers. Engineers improved coolant flow through revised cylinder head castings and optimized water jacket design to stabilize operating temperatures. Temperature sensors monitored critical points. Thermostats were calibrated for faster warm-up without overheating risk. Coolant passages were enlarged in critical areas. Oil control also improved. Instead of chasing massive horsepower numbers, GM focused on lubrication durability, bearing life, and long-term reliability. Oil pump pressure was carefully balanced. Too much pressure wastes horsepower and can damage seals. Too little pressure risks bearing failure. GM found the sweet spot. That's a boring engineering story. It's also exactly why the engine survived, because truck buyers don't remember horsepower advertisements. They remember whether their truck started on freezing mornings, whether it pulled their boat to the lake every weekend for 10 years, whether it got them to work during a blizzard. The 4.3 almost always did, and then the real test began. Commercial fleets. Millions of miles accumulated under conditions far worse than ordinary drivers ever experience. Express delivery vans, telephone company trucks, municipal maintenance vehicles, airport service fleets, utility company bucket trucks, plumbing contractors, HVAC technicians. Some accumulated over 300,000 miles with only routine maintenance, oil changes, spark plugs, water pumps, occasionally an intake manifold gasket. The bottom end usually kept going. Fleet managers started doing something unusual. They began specifically requesting the 4.3 when ordering new vehicles. Not because it was the most powerful option, not because it was the most sophisticated, because downtime cost money, and the 4.3 minimized downtime. A telecommunications company in Texas documented their experience. Over 50 trucks, average mileage exceeding 280,000. Total engine replacements? 3, and 2 of those were from accidents, not mechanical failure. Independent mechanics became so familiar with the engine they could diagnose many problems by sound alone. A rough idle? Check the spider injection assembly. Coolant disappearing? Inspect the intake gasket. Random misfire? Look at the distributor cap. Slight knock on acceleration? Probably carbon buildup. Try premium fuel or a cleaner. These became almost routine because the engine itself rarely suffered catastrophic failure. There were no mysterious gremlins, no unexplainable issues that required engine replacement. Problems followed predictable patterns. Of course, it wasn't perfect, far from it. The central sequential fuel injection spider assembly developed a reputation for sticking poppet valves. Fuel delivery became inconsistent, causing hard starts, rough idle, and lean misfires. Plastic intake manifold gaskets on certain model years sometimes deteriorated, allowing coolant leaks. The gasket material couldn't handle the thermal cycling over hundreds of thousands of miles. Coolant would seep into the valley between cylinder banks, sometimes mixing with oil, creating that dreaded chocolate milk appearance in the crankcase. Distributor caps mounted low at the rear of the engine could collect moisture, particularly in humid climates or during deep water crossing, causing random misfires that disappeared once everything dried out. None of those problems were ideal, but here's the difference. They were fixable, usually without replacing the engine. A spider injection repair kit cost a few $100s. An intake gasket replacement was a weekend project for experienced DIYers. A new distributor cap cost less than $20. Owners accepted them because once repaired, the engine often returned to another 100,000 miles of dependable service. That's a very different kind of reliability than perfection. It's survivability, it's forgiveness, it's the difference between an engine that demands perfection and one that tolerates the real world. Meanwhile, the engine expanded far beyond pickup trucks. The Chevrolet S10, the GMC Sonoma, Astro vans, Safari vans, full-size Silverado pickups, Tahoes, Blazers, marine applications, industrial generators, even forklifts, motorhomes. The variety was staggering. Marine versions became particularly respected. Operating under constant heavy loads for hours, many produced between 220 and over 300 horsepower depending on induction and calibration, while delivering strong low-end torque that pushed heavy boats onto plane with surprising ease. Marine engine builders made specific modifications: corrosion-resistant coatings, closed cooling systems in saltwater applications, specially calibrated ignition timing. Saltwater environments destroy weak engines. The combination of heat, moisture, and salt creates conditions harsher than any road application. Engines that survive marine duty prove their fundamental engineering strength. The 4.3 kept earning trust. Fishing guides in Louisiana ran them hard. Lake tour operators in Minnesota accumulated thousands of hours. Sport fishing boats in California depended on them. One marine technician in Florida reportedly summed it up perfectly. "It doesn't care if it's Monday or Saturday, just give it oil." That became its unofficial motto. But there was another reason GM refused to abandon it: money. Developing an all-new truck engine costs billions of dollars. Existing production tooling for the 4.3 had long been paid for. Manufacturing processes were perfected. Replacement parts existed everywhere. Every dealership knew how to repair them. Fleet operators trusted them. Why replace something customers already believed in? Automotive accountants love proven platforms. The development costs were amortized decades ago. Every engine sold was nearly pure profit. The parts supply chain was completely mature. Manufacturing defect rates were minimal. It made perfect business sense. Then the world changed again. Ford introduced modern modular V8s. Toyota expanded truck production with ultra-reliable powertrains. Nissan brought sophisticated V6 technology. Turbocharged engines began shrinking displacement while increasing output. Direct injection became common. Variable valve timing spread across the industry. Cylinder deactivation arrived. Many older engines disappeared forever. Yet somehow, the 4.3 adapted again. In 2014, GM introduced the newest generation, known internally as LV3. Calling it the same engine would actually be unfair. It shared the famous 4.3-liter displacement but incorporated advanced technology that engineers in 1985 could barely imagine. Direct fuel injection delivered gasoline directly into each combustion chamber at pressures exceeding 2,000 psi. No more port injection. Fuel sprayed directly where combustion occurred. Continuously variable valve timing optimized camshaft timing throughout the RPM range, both intake and exhaust cam phasers, constantly adjusting for maximum efficiency. Active fuel management could deactivate cylinders during light load cruising, running on 3 cylinders during highway cruising, seamlessly transitioning back to 6 when power was needed. Compression ratio jumped dramatically to approximately 11.01. That's sports car territory. Despite that high compression, sophisticated NOx sensors and precise fuel control allowed operation on regular unleaded fuel. Horsepower climbed to an impressive 285. Torque reached 305 pound-feet. That's nearly double the output of the original engine. Yet fuel economy improved, emissions fell dramatically, reliability remained strong. Most people have no idea how remarkable that really is. Imagine taking a desktop computer from 1985, doubling its performance, cutting power consumption, making it cleaner, and still having it recognized as fundamentally the same machine. That's essentially what GM accomplished. The LV3 retained the philosophy that made the original successful. Strong bottom-end torque, durability before glamour, simple packaging, reasonable operating costs. Truck buyers appreciated every bit of it. Performance numbers reflected that philosophy. Silverado models equipped with the LV3 accelerated from 0 to 60 in roughly 7 seconds depending on configuration. That was genuinely quick for a full-size work truck. Maximum towing approached 7,600 pounds in properly equipped trucks. Payload capacity remained strong. For many buyers, that was all the capability they would ever need, and it came wrapped in decades of proven engineering knowledge. So why didn't GM simply replace it with a turbocharged 4-cylinder? Because work trucks don't live on spec sheets. They live on job sites, in dust, in mud, in extreme heat and bitter cold. Turbochargers create additional heat, higher cylinder pressures, greater complexity, extra maintenance concerns over very long service lives, more components that can potentially fail. The naturally aspirated 4.3 remained predictable, easy to service, and trusted. That trust became one of its greatest engineering achievements. Today, original first-generation 4.3 engines with well over 300,000 miles aren't mythical internet stories. They're real. You can find them in rural America, in small towns, in commercial fleets. Many still start every morning, many still tow, many still earn paychecks. Mechanics often say regular oil changes matter more than anything else with these engines. Keep clean oil flowing through the bearings, change it every 3,000 to 5,000 miles. Don't stretch intervals just because modern oils claim you can. Prevent overheating. Watch the temperature gauge, replace thermostats before they fail. Replace worn ignition parts. Don't ignore a misfire. Change spark plugs on schedule. The engine usually rewards you with extraordinary longevity. Some owners report engines exceeding 400,000 miles, still running, still working, still dependable. Eventually, though, even legends face change. Modern emission standards continue becoming stricter. Electrification is reshaping the entire automotive industry. Battery-powered work trucks are slowly entering commercial fleets. Hybrid technology is expanding. Large naturally aspirated engines face increasing pressure from regulations rather than reliability. Production numbers have inevitably declined compared to the engine's peak years. The newest GM trucks increasingly feature turbocharged 4 cylinders, advanced transmissions with 8, 9, or even 10 speeds, technology that was science fiction when the 4.3 first appeared. Yet the 4.3 quote's influence remains everywhere. Its design philosophy helped define GM truck engineering for generations. Its architecture proved that durability often matters more than headline horsepower. Its millions of production units created one of the largest aftermarket support networks in automotive history. Replacement parts remain abundant. You can walk into almost any auto parts store and find what you need. Performance upgrades are everywhere. Aftermarket camshafts, performance cylinder heads, intake manifolds, exhaust headers, supercharger kits. The aftermarket treated it like the V6 equivalent of the small block V8. Marine builders still respect it, hot rodders still modify it, fleet mechanics still trust it, off-road enthusiasts still swap them into lightweight vehicles. Collectors may chase big block Chevrolets and legendary LS engines. Those get the magazine covers, the auction house attention, the enthusiast worship. But the humble 4.3 quietly built something arguably more impressive, a reputation, not for speed, not for power, not for prestige, for showing up every single day, for decades, because the greatest engines aren't always the fastest. Sometimes they're the ones that simply refuse to quit. That's the hidden truth behind the GM 4.3 Vortec V6. It wasn't the most powerful engine GM ever built. It wasn't the most advanced when it debuted. It never won prestigious awards or broke performance records. But through smart engineering, constant evolution, and an obsession with durability, it survived for roughly 4 decades while countless competitors disappeared into history. While exotic engines came and went, the 4.3 just kept working. While manufacturers chased horsepower wars, the 4.3 focused on reliability. While engineers designed increasingly complex powertrains, the 4.3 remained fundamentally honest. It never pretended to be something it wasn't. It was a working-class engine, built for working-class people, doing working-class jobs, and it did them extraordinarily well. If you enjoyed this deep dive into one of America's most underrated engines, let me know in the comments what forgotten engine or legendary rivalry you'd like to see next. And make sure to subscribe so you don't miss the next story, because sometimes the most ordinary machines end up telling the most extraordinary stories.